And so the actual typing of stuff you have to do isn't changed much. But if you go to parallel, like you guys want to do parallel, this is the kind of thing I have to type when I'm on Ravel, or Ravel, I don't know how to pronounce it. But you compile, and then I basically do a preemptive login to all the machines, and then I do an MPI run command. And I have to tell it the number of processors I'm requesting, and there's this machine file where I ask the number of which machines that I'm requesting it from. And each machine, you know, it's got all these nodes, and each node has 4 processors. So there's, in this file, I have the names of 8 different machines on the Ravel cluster. And so 8 times 4 is 32. So I'm requesting 32 processors. And so anyhow, it's a little bit more involved. This is the run command, and you include the, here is the OceanM, the actual executable, but you have to throw in MPI run at the executable with a request for a number of processors. And I'll send you this file so you can see, you can just copy this verbatim, changing it to your own directory. And I actually wrote up a little script for myself so to check that the number of processors I'm requesting is consistent with the number of machines in the machine file, and that's consistent with the number of tiles in the ocean.in.
So machines is a file then?
Yes. Yeah, so for example, it's just a text file with the list of the number of list of the names of the nodes on Ravel. So I don't know if you guys probably do a different setup, and I'm really curious to find out how the setup would be different for you guys when you're doing it with the Kudo and the NVIDIA software. If it compiles well, you'll see at the very end you'll see that it is built. The last thing it built was something called an Ocean S. You can go into build.bash and change a switch so that it runs, it changes it into a debugging mode, and then it runs Ocean G. So Ocean G runs in serial and is for debugging purposes, but Ocean S is for serial. So it runs on one processor. And when you run it, it might look like this. Ocean S, and you input external ocean upwelling.in. So you tell it, this is my input file, so in ocean upwelling.in as the input parameters, and you send it to Ocean S, and this is what it would look like. It spits out a bunch of stuff up there, and here it's computing the history file. So then each of these time steps, so see every 5 minutes, it's outputting a file. It's really coarse resolution, so it zips through this thing pretty fast. And it gives these diagnostic numbers like total volume and total kinetic energy and total potential energy, just so you can get a feel for it. You want potential energy and kinetic energy to be kind of constant. But the important thing is it's computing these things. These are time. This is days and hours and minutes and seconds. And so there you go. Oh, it wrote out something into a file. So this is what it looks like. So it'll zip by and you'll miss it. Or you can pipe it to a log file. When you pipe it to a log file, let's see, is it worth it my showing you what it looks like? So just to show you what the log text file looks like. Oops. Sorry about that. Gives you a lot of information. I want to point out something at the end that it gives you ideas on how much time it's taking in different parts of the code. A lot of the stuff is sort of self-explanatory. It tells you every possible bit of information, the subversion, the version of ROMs you downloaded, what your header file is, so you can debug stuff. What it thinks the loop root is, what it thinks this header file is. There's a parallel threads 1 because it's in serial, tiling 1 by 1. You can control how it splits up the tiling horizontally. So then here are all these parameters, the number of output times, the delta t. And at the very bottom of this, after it runs successfully. So here we see we were staring at it as it was going through this time stepping here. But let me zip to the very bottom after it finishes. This gives you information like when it's done, and that's nice. When it's done, it tells you how long it took, and it tells you how much, it gives you a time profile. So this sort of thing, if we're going to optimize for speed, these parameters are the sorts of things maybe you guys might be more interested in than I usually am. Tells you how much time it spends in different parts of the code. It gives it in terms of percents, and I think in terms of seconds, and a grand total number of seconds.
When you run it on with finer grain resolution, does that one model 2D kernel, do they all scale basically the same, so that still takes up about 74% of the runtime, or does that become much bigger?
That becomes, it becomes less. How does it scale differently? When, that's a really good question. But it doesn't scale, it's not an obvious, simple scaling. And it depends sensitively on this internal time step and the external time step. The internal time step is, or rather the fast time step is for the surface waves. If you have the fast time step being really, really teeny, then you're taking many, many, many time steps for just the 2D kernel is supposed to be the two-dimensional, just the surface waves. So this tells me that if I can at all get away with having a larger time step for the fast time step, then that'll really help, for example. So the 2D kernel, 3D equations, predictor step, predictor and corrector. So then the 3D equations take a whole lot less time, say. But yeah, so there's some information there that might be useful, and that gets spat out automatically. Let's see. Let me go back to my plan. I could show you what this looks like on Rattle. Let's see. Let me just finish this, and then we'll see what kind of questions you guys have. Okay, yeah, so the ratcheting up the level of complexity, there's the data assimilation run, or rather the upwelling run, where everything is done internally. The bathymetry and the wind stress are all internal. And then another level of realism is where the bottom bathymetry and the wind stress are read in as files. Another level of complexity is where you then assimilate data into the run. So you have initial conditions, and you have boundary conditions and wind stress forcing, and you do a run. I know what I want to show you. I want to show you what it kind of looks like when you're done. It looks kind of like, so here I have some ROMs, or here I have some MATLAB plots, just to give you a more intuitive feel of what's going on. Here we have this is the coastline near us. San Luis Obispo is about there. This is Morro Bay. This is Avila Beach, and say Arroyo Grande is down here. And here's some bathymetry. So this is like a model. This is a really coarse grid. This is like a depth of 100 meters. This is a depth of 800 meters down here. And we have some really realistic coastline in here, such that I think we can even have the, if I zoom in, we even have the, this is the Avila Beach Pier is in the data set for the coastlines. And this is our Cal Poly Center for Coastal Marine Sciences Pier. And there's a breakwater. Anyhow, that's in there. So there's my bathymetry. What I'm going to do is show you some results of some simulations, and I'm just going to show you an animation to get a feel for what's going on. Here's some depth average velocity. So it's going to show up nicely. Again, just to give you an intuitive feel, this shows you what the wind direction is somewhere out here. The wind doesn't actually vary much, so it gives you a good idea of what the wind is doing over the whole domain. And this shows you the depth integrated velocity. And you can see the wind kind of changes day to day. This is like every quarter of a day snapshots. So it's been going on for 10 days now, 10 and a half, 11 days sort of thing. And when the wind weakens, you'll get more northward flow. Right now you can see a kind of recirculation here, and kind of a flow going up this way. You see what I mean? You need to specify what's going on. The boundaries, we needed an initial condition, and see when the wind dies down, wind is gone, whoosh, there's this northward flow back northward. So that's This is the kind of thing we get out of ROMs. Simulate the ocean for a little while, but who's to say that this is reality? You know, this is from one grid cell to the next, 400 meters. Between here and 400 meters from here is a lot of water. There's a lot of stuff going on in the subgrid scale, and no matter how fine resolution you get, you're not going to capture it all. Why do we have it at that coarse grid scale? Because it just runs too slowly if you've got it on a realistic time scale you really want. So, and that's where parallelization comes in to make it run faster. And the other thing that you can do to make it run more realistic is you can go out to the ocean and measure what's the current here, what's the temperature here, what's the salinity here, and then tell your ocean simulation, hey, by the way, right here, you think the temperature is 10 degrees, or whatever, sorry, I was in Celsius. You think the temperature is in, 10 Celsius, but it's actually 15 Celsius. And so then you can correct your code. However, if you just go in and say, delete 10 and put in 15 instead, it makes all of the fields discontinuous, and there's these waves that propagate and things go nasty. So instead you have to carefully roll the data in. And it turns out, to do this properly, increases the length of time it takes the code to run by an order of 20 to 50 times, because you have to iterate. So we're calling this the forward run, where we just start ROMs running and let it run for the length of time we want it to run. Turns out the right way to do it is to run it forward in time, and you sort of run like an associated model backwards in time, along the way seeding it with the data. And then you run it forwards and backwards in time again, and iterate until you converge. So, and the iterations, ideally, you iterate as many times as you have pieces of data, but it gets better than that. So you typically go 20 or 50 or 100. So 20 or 50 or 100 times longer than it takes for you to run just the quote-unquote forward model. That's how long it takes to run the data assimilation model. So that's what I mean by it takes 20 to 50 more times CPU to do this data assimilation run. And here, parallel computing is absolutely essential. You can learn a lot. You can do a lot of science with just the forward model. Change the bathymetry, change the, like I recently did a paper where we looked at the bottom slope. We changed the bottom slope, and our theory predicted that when there's upwelling winds, that the water below should be more surface intensified for deeper slopes. And you can do these sort of thought experiments, and you can do these. You can play God with the ocean and see what happens. But if you want a realistic run and you want to assimilate data, the amount of time it takes to run these things is really